Hello and welcome to this Amatech Land Incorporated webinar. My name is Rich and I'm a Senior Manager with IHS, and I'd like to review just a few housekeeping items with you before we begin. Let's take a moment to familiarize ourselves with the operation of the user interface for today's webinar. Now, the large window that you're currently viewing with the heading Amatech Land Presentation in the upper left, that's the primary window for today's webinar. Now, you should be seeing the welcome slide there right now. Now, if you look to the right of that main presentation window, you'll see the speaker's bio window, and that contains background information on today's presenter. Now, just below that, there's a Q&A window, and at any time during this presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will then be placed in a queue for our speaker to address when we get to that Q&A session. Now, if you look to the bottom of your screen, you will see additional buttons to enhance your webinar experience. If you'd like to see what a particular button does, just hover your mouse pointer over it and a tooltip will appear with a description of that button's function. And now to get things started, I'd like to introduce the Global Product Manager, Richard Gagg. Richard, go right ahead.
Good morning. Today I'm going to talk about the Land NIRB borescope thermal imager and its use in the glass industry for measurements in the glass melt tank. There are many needs for accurate temperature measurement and imaging within the glass melt tank. For instance, campaign life extension. Critical refractory surfaces such as those around the port arches are continuously monitored. Crown temperatures are long-term temperature trended. This allows optimization of reversal times and longer refractory life can be achieved. In glass production efficiency, the blanket, melt line, and batch transit time can be visualized, recorded, and compared. For energy efficiency, burners can be optimized from viewing their propagation and burn efficiency and their impingement onto various areas. Structural issues can also be determined. Early temperature visualization of cold spots in the refractory walls, possibly indicating air leaks caused by structural issues, can be detected. A wide variety of sensors are available for temperature measurement in the glass tank. These can be broadly split into two areas: contact devices such as thermocouples and non-contact devices such as infrared devices. Contact measurements, typically thermocouples, the sensor consists of a junction of two dissimilar metals which when heated produce a specific voltage for a given temperature. Non-contact temperature measurement, radiation thermometers. These types of instruments measure the heat or the radiated infrared energy from an object by focusing this energy through an optical system onto a detector. The signal from the detector is then related to a temperature by a series of signal processing functions. All objects above absolute zero emit energy, and the hotter the object, the more active its molecules are, hence the more radiated energy it emits. In this graph, we see that the peak of available radiated energy shifts towards the short wavelength end of the spectrum as temperatures increase. At low temperatures, little or no short wavelength energy is emitted, and you have to select longer wavelength detectors to make those measurements. Conversely, at high temperatures, plenty of measurable radiation is available, and short wavelength detectors can be effectively used. Non-contact radiation thermometers and thermal imagers are designed to respond to wavelengths within the visible and the infrared portions of the electromagnetic spectrum. In practice, these thermometers typically operate over portions of the spectrum between about 0.5 out to 14 micrometers. The human eye is responsive to radiation emissions within the visible region of the spectrum, which is around 0.65 micrometers. A radiation thermometer can only measure what it sees. Smoke, steam, Dust, solid objects in the sight path of the thermometer will reduce the radiated energy from the target and should be avoided wherever possible. This diagram shows transmission of radiated energy through the atmosphere. As we can see from the white areas, there are certain wave bands where transmission is very poor. In these regions, typically water vapor and carbon dioxide in the atmosphere absorb some of the infrared energy. The actual amount of absorption is dependent on the path length and the concentrations of those vapors. It's important that thermometers are not designed to operate at those wavelengths where there are atmospheric absorption bands. Thermometers are usually designed to operate in what are known as atmospheric windows or bands, where the transmission is very high. Such regions exist around 1 micrometer, 1.6 micrometers, 3.9 micrometers, and 8 to 14 micrometers. It is common for thermometers to have a filter in front of the detector to ensure the spectral response is matched to an atmospheric transmission window. Now let's talk a little bit about emissivity. When radiation from the interior of a body reaches the surface, some is emitted and some is reflected. The same thing happens to the radiation incident on the surface and to the same degree. Thus, the radiation leaving the surface is the sum of the emitted radiation plus that reflected from the surrounding background. The former depends on the temperature of the body, the latter on the average temperature of the surroundings. The thermometer cannot distinguish between them, and the indicated temperature will therefore depend on these two temperatures as well as the reflectivity and the emissivity of the surface. It's important to understand the emissivity values of the materials within the scene. These are factors that can affect the emissivity of a target material. The surface condition of the material, whether it's rough or smooth, the viewing angle onto the material, whether it's normal or some glancing angle, the actual temperature of the material's molecular structure, and finally the wavelength at which you measure the material. These are all factors which influence the emissivity, and they need to be understood before one can accurately measure temperature within the scene. Molten glass is virtually opaque in the short wavelength infrared spectrum, unlike when it is cool, where it's transparent. Thermometers which measure glass are chosen based on the glass temperature and also the glass thickness. With low temperature glass, where you can typically see through it with the human eye, we typically choose a waveband based around 5 micrometers, where the glass is opaque. If glass is very, very thin, under a millimeter, then you may choose a 7.9 micrometer wavelength to see that low temperature thin glass. With molten glass, we don't have these issues, and we can choose an accurate 1 micrometer thermometer. Typically a 1 micrometer thermometer looking at clear soda lime glass at 1400 Celsius will see into the surface approximately 18 millimeters. So it's perfect for measuring bulk glass temperatures within a glass tank. So here we see a Land NIR-B borescope thermal imaging camera, which is inserted through the furnace wall, looking into the glass tank. From the schematic, you can see that the cooled lens tube penetrates both the furnace wall and the internal refractory and sits slightly recessed into that refractory. The imager is fed by cooling and air purging surfaces which keep it operational in the very high ambient temperatures and the furnace temperatures that the lens tip will see. So here we have a schematic of a typical side-fired glass melt tank. The position where one would usually mount one of these thermal imaging devices would be high on the bridge wall, angled slightly downwards, looking into the tank. In a typical thermal imager installation like this, it would be mounted on an auto retract mechanism. The auto retract mechanism will automatically remove the imager should it sense an over temperature condition or sense a lack of coolant or air purge flow. Here we can see two different installations of the Land NIRB borescope imager. Both of these are on the bridge wall, mounted high, looking slightly downwards. The picture on the left is one of an imager on a permanent installation with no retraction mechanism involved. The second image on the right is one of the same type of imager but mounted on an auto retract mechanism. This is the one most commonly used for these applications, as it ensures the safety of the equipment that is imaging and measuring temperatures within the tank. Here we can see a typical thermal image taken with the Land NIRB borescope imager. This is of a side-fired glass tank. We can right now see that the tank is being fired from the right-hand ports and exhausted over on the left-hand ports. In this particular case, the operator has set a multi-segment profile line along the crown of the furnace, measuring crown temperature. He's also set two profiles at the bottom of the screen where he can detect the glass matte and if it has fully become homogeneous. Because of the near-infrared nature of this imager, one can also see the flame patterns, the flame size and propagation, and effects within the tank that are being influenced by those burners. Here's a Land NIRB imager looking into an end-fired glass tank. You can see here that right now the tank is being fired from the right-hand port. The video image is a live image, refreshing 30 times a second, just like a video camera, but also giving you full temperature measurements anywhere within the scene. A DVR function within the software can save time-lapse videos, which make it very easy to detect and spot developing trends. So let's summarize what we've seen. The NIRB thermal imaging camera provides the best accuracy temperature measurements of the multiple materials that we find in glass tanks. The very wide angle through the wall borescope lens sees a 90-degree field of view, allowing you to see both the materials within the tank refractory materials, the crown, the port arches. So it gives you very good measurements of the glass itself, of the critical refractory materials, and also gives you a visualization of what is happening within the tank so that you can detect trends, see flame patterns, detect cold air infiltration that might be caused by a crack in the structure. NIRB allows you to increase efficiency of the furnace through its continuous temperature measurement and long-term data trending functions. I'd like to thank everybody for attending today's webinar. I know that your time is important. For additional and current information on LAN's NIRB thermal imager, please visit our website at www.landins.com. At this point, the presented part of the webinar is ending, and we are now opening up for questions. Thank you very much.
And thank you very much, Richard. Now, before we get to the question and answer section of this webinar, I'd like to remind all of our attendees that if we don't get to your question, don't worry. The complete Q&A transcript, including answers we did not have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into the on-demand mode. Okay, now let's get to those questions. Here's your first question. How large does the hole have to be through the wall?
Okay, the probe diameter is 64 millimeters. And so the hole in the furnace wall needs to be just a little larger than that for clearance issues.
And here's your next question. What's the expected life of the device?
I don't know if this is answering your question, but the NIRB has a 36-month warranty. So we fully expect it to last longer than 3 years. I hope that helps.
And very simply, what are the power requirements for this?
Well, both the NIRB and the auto retract mechanism operate on low voltage DC, 24 volts DC nominal. So there's no requirement for mains voltage.
Okay, let's take a look at another question. What services does the device need?
Okay, I'm assuming you are asking about things like water and air supplies. In the case of the cooling purge air flow, that is around 15 to 16 cubic feet per minute. And to achieve that on the NIRB, that requires about 20 psi of pressure. The cooling water requirement is approximately 6 gallons per minute. And the cooling water should be under 40 degrees Celsius.
Okay, great. Thanks for that answer. Let's take a look at a few more, shall we? Is the NIRB available in NTSC or PAL video outputs?
Okay. Well, a few years ago, thermal imagers used to have analog video outputs like NTSC. But in the last few years, most industrial imagers have gone to digital. And so in this case, our NIRB imager, the output is gigabit Ethernet. There's a couple of advantages to that. The first is you can use standard gigabit cables, so Cat6 cables, gigabit switches, and the connection to a computer is through a standard RJ45 Ethernet port on the computer. The other advantage to that is that the Ethernet standard is a global standard, so there isn't any need for different analog device standards like the old PAL and CCAM and NTSC that were used in different countries. So now it's a universal global gigabit Ethernet.
Okay, let's take a look at another question about where do we locate the computer?
Well, the computer is usually located in the control room, and distance to that control room is no problem because we connect using standard Ethernet. So we can either use Cat6, copper Ethernet cabling. If we go over 100 meters per segment, then you would just use switches between each segment. Or you could use fiber Ethernet and then you can go kilometers without requiring switches. We can also provide client software, and client software runs simultaneously in other locations on other PCs. So, for example, the control room could be viewing the thermal images, and at the same time, an engineer in his office can simultaneously view live images and information in his office.
Okay, we've got time for one more question. Is it possible we can get a demonstration at our site?
Well, yes, certainly. We've got demonstration systems that we use for this purpose. We would typically come out for one day and view the furnace through a temporary opening. We would need water and air to be available during that demonstration, because we're going to have the tip of the borescope inserted into the furnace wall. But we'll bring pretty much everything else. So we'll bring cables, a notebook computer with the software running on it, and the power supplies necessary for the equipment.
And with that, we're going to have to wrap up this webinar right there. Richard Gagg, thank you for sharing your expertise and spending some time with all of us today.
So again, thank you very much. If anyone has additional questions after this webinar, you can certainly email me. My email address is richard.gagg, that's Gagg, at Ametek, that's spelt AMETEK.com. And I do appreciate you attending. Thank you.
And a special thanks to all of our audience members for being part of this webinar event. Now, as a sign of our appreciation, one lucky attendee, drawn at random from all of our registered attendees who complete the survey at the end of this webinar, will receive an iPad Mini 3. So good luck to everyone. Now, we would also like to let you know that you'll be receiving an email from us with a link to the on-demand version of this presentation, a PDF of this PowerPoint, an FAQ document, and a Q&A transcript. Lastly, please take a moment to complete our survey, which will appear on your screen at the end of this webinar. Remember, you must complete the survey to be eligible for the iPad Mini 3. Again, thanks for taking the time to be part of today's webinar event. Take care, and we'll talk to you soon.